participants to the exhibition and the conference NEVA 2023. Let's open up this event. We were honored to be the first international strategic session of the conference and exhibition NEVA 2023 under the title Marine Robotics Projects and Practice. At the outset, I would like to say that we are long-standing partners to the NEVA exhibition. We are familiar with all of the participants of this exhibition. We know NEVA International, the organizer of this event in St. Petersburg, as well as in other cities of Russia. This session starts the business program of the exhibition, and we are especially honored about that. So we are grateful for the honor and we appreciate it. It is not our first time at this venue, at this platform, and we were also participants to the Marine Congress in Moscow. And on top of that, there was a target session within the framework of the PAMIS conference, jointly with NEVA International. To us, the NEVA, the organizers, the St. Petersburg Marine Technical University, the Marine Academy, named after Krylov, value cooperation with NEVA very high. We believe that this partnership is for mutual benefit to us. NEVA is an excellent team of organizers, professionals who promote our technologies and research through their events. For NEVA, this is just content because they are managers, they are organizers, so they get contact as a benefit from us. Therefore, I believe that this partnership is mutually appreciated. Now, let's start a short video footage about NEVA. And before we demonstrate this video, I would like to extend my gratitude to the NEVA organizers, and especially I would like to appreciate the efforts by Anastasia Demidenko, program director, and Anna Burakova, the lead manager of the conference. It is thanks to them that we are having this session today. Thank you, girls. Now let's start the video. Colleagues, let me introduce our panel. Natalia Zorlina. She represents the wonderful company Vertowing, one of the companies that belongs to the Vertowing Group. Ilya Kostandi represent Tetis Pro GAC, another very prominent company. My colleague and friend, Mr. Rizhov Vladimir, he's an expert, St. Petersburg State Maritime Technical University. He's head of the Department for Mathematical Modeling. Please welcome. Viktor Tarasov represents the Russian Maritime Register, and today we believe that drones and unmanned aerial systems should be certified, so it is him who is actually responsible for this certification. And our long-standing participant is Lyubov Martynova. She represents a very exciting company, Electropribor. I think that your full name is Central Research Institute, Electropribor, or Electrical Facilities. Mr. Vlasov is the next, a very well familiar personality, Oleg Vlasov. He represents our design company. He's the submarine designer. And today, well, Malachite, this enterprise, plays a very important role in robotics and in applying robotics to underwater environments. Yes, thank you. And Dmitry Olegovich, Dmitry Motorin, he's head, chief designer, JSC Central Design Bureau of Marine Technology, Rubin. Well, I was delegated to moderate this session. I'm responsible for international cooperation in the area of education, St. Petersburg State Marine Technical University. So we can start. We have a very packed agenda. We have presentations, 10 slides long. Our first speaker is Dmitry Simonov. He has 10 minutes, and others have 7 minutes each. We're going to ask questions in the chat. So a Q&A, live Q&A here is not planned, and you have all the chats in the program. So I think that we can start. Dmitry, please, let's have the presentation by Mr. Simonov. It's indeed great to be the first one, because you have 10 minutes instead of 7. Distinguished colleagues, I'll do my best to fit into the time limit. Today, I'm going to deliberate a little bit in a broader way. And I'm also going to master how to operate the pointer. Our company has been for a few decades in this area, and we have some experience accumulated already. So let's think about what kind of topic that is. Starting from 1963, this is our hallmark year. We believe that the exploration of the ocean and the seabed using AI appeared. And then large companies, UK-based companies, and then other international companies joined in, and all started with some small-scale research by small-scale teams of engineers. And then the entire evolution of this process matched any evolution on Earth with other researchers, engineers, scientists jumping in. And today, 30 years after, robotics in marine industry is already a commercial industry. We have first designs, we have developments, and today those satisfy the demands of ministries. Today we've got General Dynamics, Kongsberg, that have accumulated international experience in a variety of areas. So these images are very well known to all of you. All of these facilities and machines are already in commercial production. Likewise, any other areas, Russia is lagging behind by a decade. Approximately, the founding father was member of the Russian Academy of Sciences, Ageyev, who worked in Vladivostok in a respective research center. The next 30 years to follow, this center was an only designer and specialized center for these technologies. In the end of 80s and 90s, remotely operated machines were developed, and some time after, when more research universities were involved, after 2010, we started to explore this topic jointly with our partners like Rubin, Electropribor, Aurora. All of those are very well present in the market already, and we are exploring technology today. I'm going to talk about the trends and the impediments that we are encountering, because we're always rushing back. We're always trying to keep up. And that's what limits and constrains our activities. You can see the recent designs and developments. I mean, the technologies are going on, there is advancement, but once again, the advances demonstrated by our Chinese partners are indeed tremendous. Those are extraordinary. It can be envied by international producers. Initially, China was some 2 decades behind the international agenda, but today China is at the forefront and has outperformed the US and other countries. When we approached the Marina Dench, we remember that we started to receive a lot of information and about Chinese unmanned machines exploring the Mariana Trench in an autonomous mode. And international newspapers wrote a lot about that. Our partners from China in this respect demonstrate unprecedented growth. This variety is indeed fascinating. What's the cause behind that? Here you may see a very brief analysis of international sources. The market of underwater robotics amounted to $3.7 billion. As for its growth, it is projected to undergo 1.5-fold growth. This is the statistics of 2018, and the incremental growth is indeed tremendous. It is subjected to geometric progression, and robotics is just only 1/3 out of all that. So what's going on now in the world globally? What do we see now? As the previous graphs showed, everything starts from the makeshift designing that then turns and expands into some kind of a commercial project. And once this commercial project expands to an industrial level, then the cost of commercial robotics is lower than military robotics, because we understand that the safety, the resilience, the robustness is different there. Therefore, the advancement of military technology versus what we used to have 30 or 40 years ago is based on commercial technologies. This is what's going on internationally. What happens in Russia? Well, I'm going to refer to our own experience, but I don't think that this makes us very much different from the others. Starting from the 2000s, we fulfilled the orders by the Ministry of Defense based on the R&D that we used to have. All our peaceful R&Ds provided us with absolutely free access to international AI, international equipment, and spare parts. Based on these achievements, we started to produce military technologies. And today, when this pyramid, starting from 2014, due to reasons very well known, is becoming ever more fragile, we see that in 2014, the next year was 2018, and 2 years ago, almost all the international developments became inaccessible to us. So what we are left with, these are the developments that used to be here at the beginning of 2000s. So the variety has shrunk to just a few. What remained is hydroacoustical systems for hydro location, hydro surveillance. There is also hydroacoustic search equipment. Let's look at the variety of models. If you have access to this equipment, you would feel yourself indeed robust and resilient. And this is what we used to have 20 and 30 years ago back. That's the situation we are in now. Our designs expand far beyond what is on the slide, and you will be able to see the majority of them at this exhibition. So let's do our best so as to rapidly fulfill these gaps, because today we are suffering a huge deficit in spare parts. Here I mean not only hard and software, but I also mean technologies. This is the key component that ensures our success along the pathway of development and AI. However, our keynote designs are already domestically produced, and we have an array of national enterprises that actively participate in these programs. We understand that our current level of development, and here I believe that robotics and technology and AI are just the same thing. So today we are at the very beginning, and we are yet to move down the road quite along. And it's going to be a very complicated way for us. However, without the designs that I used to mention a few slides ago, I believe that so far it is very challenging to use these technologies jointly with some complicated, sophisticated equipment, because this technology looks like a computer game so far. So I believe that I should move over to conclusions. We understand very well that we are amid a critical situation today, And we have to explore our investment potential. We have to do our best considering our insufficient investment potential. So our colleagues from Aurora are doing their best to promote autonomous and remotely controlled machines. But those are small-scale technologies. They haven't yet been implemented on a larger scale, and this actually holds our performance and progress. So far, we do not have our domestic consumers. Who are they? Because ultimately, our target is larger projects of a larger scale and not small-scale projects. We would like to extend into the mining industry, for example. However, we do not see any kind of advancements and any active demand for our technologies. At the bottom, you can see a heavyweight machine, remotely controlled machine. For the fourth year, its designer is trying to adjust this machine for Gazprom and for its specific programs. And regrettably, on the first slide, we were able to see some positive things. But today, in terms of demand, we can demonstrate only 3D models and just support letters.
These support letters, they relate to Gazprom, to Rosneft. Everybody understands that for a long time, knowing the fast velocity of oil field maintenance and equipment, our oil and gas industry used the advanced resources from our international partners, using not only their equipment, but their services. In Russia, we have Hydro-bionic company, and it is backed by some other companies. But this company is one of the most prominent and successful that competes quite successfully with our former international partners that left Russia a year ago. Hydro-bionic and some other companies are ready to deploy their efforts here, but we don't have Russian equipment that would allow us to provide successfully services to our own gas companies. So talking about civil equipment, the first demanders are oil and gas companies, and then we'll have other companies like that need to service the Northern Sea route, mapping, geological surveys. There are a lot of questions, including scientific ones, that show high demand in maritime robotics services. So the foundation has left from the pyramid, and we need to seize this crisis opportunity in order to indeed deploy this industry and create for it the foundation that was taken away from us by geopolitical situation. The industry and the science should remain the main source of the equipment of this kind. We work hand in hand with St. Petersburg State Maritime Technical University, and we understand that when we talk about design, maintenance, and construction of this kind of equipment, our higher educational establishments don't prepare their students to do. But in the nearest future, those professionals would be in high demand. Summing up my overview presentation, I would like to say, should we reverse this pyramid 90 degrees clockwise, the necessity for the even development is the sum of the market of components and their availability that cannot be created without a strong state support program, as well as the commercial demand to these products. So since our presence here at this NIVA forum, I consider that we would use this kind of platforms in order to find existing design companies and to trigger all stakeholders to participate. 10 years ago, I thought that the golden mine was maritime robotics. Today, I would like to say that the component manufacturing and software design are two gold mines within this gold market. Sorry, I took a bit more time than I was intended to, but this was Rubin, and now I'd like to give the floor to Malachite Design Bureau, the equally big design company. Friends, colleagues, we gathered here together at the first international strategic session within the NIVA conference, and forum, and exhibition. I represent Malachite Design Bureau, and we are well known by beautiful, big ships that are represented at my title slide. But we are as proud of these ships as we used to be. But following up the subject of the previous speaker, our colleagues from Rubin, I would like to say that our current trajectory started not in a garage, but from large-scale missions defined by the government back in 1965 was required to feed the country and to explore the world oceans in order to guarantee the current technical future well backed up. The equipment that has been created back then allowed to convert livable vessels into autonomous vessels, those going into the area of the robotics. Our international colleagues did the same, and if several international vessels were mentioned, 97% of all market belong to the international companies, and the reference is still in horsepowers. Well, sea versus horsepowers, and we started to understand that actually they took engines and modified engines from agricultural tractors. This is why they inherited this terminology from the conventional shore activities to submersibles. And many generations after, we still use the same terms. Malachite took the same road. And I would like to show you the results about conventional ways taken by international companies and ourselves, and the second route that we took recently, which is an alternative one. First, we need to understand, doesn't matter the road, the goals should be well understood. First, the infrastructure that is being created by Russia at the Russian Far East, like underwater oil and gas development installations, and the scale is of a little satellite city. This is something that should be created underwater. Without robotics that is ready to work 24/7, wouldn't be possible to construct an industrial city underwater. And we took this look through our clients' eyes in order to understand what should be utilized underwater. That gave us a clear understanding about what the functioning underwater should look like. Another very relevant question relates to the fact how to work with things that are installed at the seabed. This is an example about of the situation when we don't know the technology or don't understand it completely, like the first nuclear submarine. We have this heritage, but we have CARE 27. This submarine is placed at the seabed of the Novaya Zemlya, and we need to make it safe. And in order to work on it, we need robotics. Understanding the purpose of the marine robotics and comparing with international similar products, you can estimate the time that was required by the international companies to come up with platform solutions, which means equipment to maintain divers and the platform that should be the foundation of the unmanned submersibles. These are the dimensions. They allow to place inside all necessary equipment. Malekith took a similar path. Over the last 35, 40 years, we gathered a huge experience in terms of the creation of the platform equipment in order to maintain divers. We don't go deeper than 60 meters because a human being doesn't feel right when they go deeper. We can work as deep as 3 kilometers, and we can easily create a solution. But what makes Malekith is the understanding of a comprehensive approach. And Dmitry asked this question, why we don't see a huge demand. The answer is clear. The client doesn't need it as a piece of equipment. The client needs a ready-made turnkey solution because they need to understand how to use it, where to maintain. Yeah, you can buy a car, but if you have any roads or a parking lot, it would be very difficult to operate it. Malekith took this road by converting the machinery from something that we understand and using platform solutions rather, to understand what piece of equipment would be placed where. Every line on this slide has behind it a lot of components and systems, and every element should be worked on separately. So after going line by line, for us, we deep dived in every line. And on those photos, you can see industrial samples like data exchange information. Okeanis is working in this field, and it was our great pleasure to see their positive results and them being able to implement connectivity systems. These systems allow like our eyes and ears of a submersible, computer vision. This kind of equipment is present basically everywhere, onshore and offshore, summing up everything in order to accept one submersible with the size of clavecine. The information and including the dimensions are publicly available, and it is comparable with the international version. It's not a small guy, and this should be moored as well because we have equipment onshore. And I didn't mention propulsion, I didn't mention maintenance, utilization, but they are solvable. They are solvable by our company within the comprehensive approach that we preach, that we practice rather. This is exactly when a piece of equipment starts to be operational. So we shift from theoretical questions to the implementation. talking about the acceptance and the exit piece, these are practical results. We financed it ourselves, and within 4 years we piloted it in different seas in different regions, including the All-Russian Championship of Marine Robotics. The same approach was taken by our colleagues from other countries, so we followed the same path. We took ready-made solutions and we modernized them in order to make them unmanned ones. Another approach that we took quite recently, we invited our colleagues from Malachite, and these are preliminary results. We asked ourselves a question. We understand why we are creating that, but another question, what should be inside? Well, a marine robot is something that we all know when we hear it. But when we follow the road between the name of the equipment, we need to allocate some space for different systems within. So the question was, how many kilos, how many liters or centimeters we need to allocate for the guidance system. A system that makes a robot from a robot. Otherwise, it would be an automated vessel or piece of equipment, not a robot. Once we asked ourselves this question, we came up with this model. Malachite financed it on its own, so it gave us an understanding of what do we need in order for the brain to become operational. The results are shown on my last 2 slides, and this is what we managed to do. Just as with shore equipment, Malachite came up with a piece of equipment. It's tangible. We presented it on several occasions. One of its creators is Evgeny Vasilyev and Vladislav Drobatuhin, 2 of their creators, of course. They have now answers as designers, and we as engineers together understand what systems should be integrated inside a body. If we understand that, we understand how to place devices inside, and we take a look at possible solutions of 24/7 utilization regardless of the seasons. Offshore, next to the oil and gas deposits, which means at interesting markets. The results, as I said, are tangible. These are platform solutions. Where can we use them? First, the dimensions that we found are backed not only by sport ladders but also by real implementation. What results would be achieved depend upon joining forces. We invite companies that develop separate units and software to join efforts with us, because we need to be like-minded in order to come up with a viable solution. So we are walking along 2 different paths, and I hope that at next year's conference we would be able to see some results to become not only a strategic session but to be in an avant-garde of the international trends. Thank you. Thank you for your attention as well. Thank you for your presentation. I'd like to give the floor to Alexei Titov. He will be presenting using an online feature. Yes, I'm here. I'm here, guys. Vice Rector for Innovations and Priority Projects, Tatishev, Astrakhan University, very enthusiastic person, organizes all Russian competitions, and he'll be talking about a surface marine robotics. Thank you for giving this opportunity to present my own line speech. I'll talk about the Caspian region. NZ is in our 2030 program for the university. It defined necessary tools. We have two dimensions. First one, development of autonomous, remotely guided robots and unmanned surface vessels, and with small and ultra small dimensions. Here,
Right? Do you have full screen? Do you have my presentation in full screen now, colleagues? Is everything okay? Just a second.
И здесь, кроме
These achievements were done thanks to the efforts of many universities, the polytechnical universities, our university, the marine university. We were able to produce these technologies. You can see that it has got an automated operator control room. Well, we believe that this is our brand, and we have now been promoted to be one of the residents in Skolkovo, and we are receiving our resources within the framework of priority program. You may also appreciate the remotely operated underwater vehicles, 120 meters depth. We were able to develop and commercialize Prometei device for underwater surveillance at the depth of up to 500 meters. As I have already said, in our university, we've been working on this project as of 2018, and in this respect, our university is an extensive team of professionals. We participate in lots of conferences and competitions. This year we also used to have competition, and our team was top one. We were awarded the first prize. Therefore, we believe that in 2024, Rubin is going to participate in other competitions. In order to disembark from makeshift design, we decided to establish a roadmap that allows us to develop different dimensions and optimize resources. And on top of that, we were able to gain federal resources. And actually, in fact, today we are bringing together 3 universities in the area of robotics, and everyone is invited to deal with us so as to ensure that the small amount of finance that we can still squeeze into this project, we would like to extend the participation by younger teams and professionals. So our clients are also invited very kindly. Yet another area that is performed jointly with the Sevastopol University, it is called the Sea of Opportunities. Here we are going to have a set of field expeditions, and please join us. Another very important component is mainstreaming of information regarding marine robotics among school children. We create an outreach to Russian schools and disseminate information about our designs and projects. Colleagues, thank you very much for the opportunity to speak. I'm happy to take your questions, and we are currently developing an application for industrial partners of this market. Thank you so much. Alexei? Alexandra Martinova, please, the floor is yours. Electropribor Research Center. Madam Martinova is a regular speaker to our conference. Distinguished participants to the conference, today I'm going to talk about the remote unmanned control system for an unmanned vehicle that has increased autonomous capacity. Such machines can stay for a few thousands of kilometers within a few months without any external support. Jointly with the Research Center of Marine Technologies, we ensure the safety of this machine. What makes this machine utmostly vulnerable is that it may fail. You can see its parameters. To ensure its safety and to avoid failure, we need to forecast the ambient environment in which the machine operates. Especially challenging is the ability of this machine to operate in the open sea and in harsh environments and terrains. In this respect, we believe that all sorts of obstacles, like underwater rocks, fishing nets, are a specific danger to these machines, as well as surface ice that may damage the hull of the vessel. And on top of that, lengthy presence in cold water can result in preterm loss of charge in the battery, and thus the machine won't be able to arrive to its destination. Therefore, we have to be very swift in suggesting solutions. We should continuously assess the safety of this device and prevent deficit of energy resources. In this case, we decided to use BIOS dynamic network, and you can see it on the slide. We did the variability distribution with decompositions, and we were able to calculate the weight variability. What is important to know is how the ambient environment changes, what is the ambient environment like, and how it impacts the systems of the machine. In order to understand whether the external environment is safe, we should assess the operation of this device in the particular embedded environment. Therefore, we need to either reduce the energy consumption or sacrifice the capacities of this machine in terms of surveillance. We used this machine to do our survey along the Northern Sea route, and this is what we got as a result of modeling. Thus, we have some dependency between the incremental growth of the risk of danger with time of operation. We used these results to adjust the machine, and this project is a joint effort by a few universities and organizations, including the Marine Technical University. On the slide, you may see the so-called digital drilling field, where we can implement the protocols that are to be implemented on board of the design. This machine exchanges information via specific digital technologies, and you can see the structure of these technologies on the slide. We use digital twins and automated operator platform. Well, it's clear that the system cannot fall by itself. Therefore, we have specific thresholds that I mentioned at the very beginning of my presentation. Then we do the modeling. We model the task and the objectives for the machine. The machine is able to identify the obstacle, whether it is surmountable or not. Thus, the developers of the control system can validate the resilience and robustness of the operation of the machine and mitigate risks to ensure that the machine reaches its final destination point. Thus, here we looked at how to operate a highly autonomous vessel. We also looked and assessed the probability of failure and compromised resilience, and to test the algorithms. We also tested this machine on a specific rack to simulate failures. Thank you very much for your attention. I'm done.
Maevsky.
Mr. Maevsky, Okeanos Company and the Shipbuilding University have already heard about the Okeanos Company. This is the company that developed the first underwater glider in Russia, which is being successfully operated in Russia, and we know the Shipbuilding University very well indeed too. Distinguished colleagues, I would like to present my presentation. Today I'm going to talk about group monitoring systems to be able to do monitoring and surveillance of the aquifer. I'm going to talk about the practical implementation of our technologies. Currently, there is a variety of projects that are based on group network operation of different systems. We know that drones can be integrated into such networks. We also, in Moscow, have a number of such projects. The projects that we have here are homogeneous. The technology is indeed broad, and previous speakers today also mentioned the tasks and objectives of this technology. First and foremost, the technology is based on AI that allows us to very accurately build predictions. On top of that, AI can also facilitate relocation. Therefore, the AI is at the crossroads of robotics. As mentioned, groups can be different. Those can be the same, they can be different. On this slide, you can have heterogeneous robotic technologies. The US, where gliders are used to assess the situation with the aquifer, British colleagues who do monitoring and ensure solutions to the engineers. We need to develop effective remote control systems. Those are mentioned in the documents presented on the slide. Here you may see that Russian underwater autonomous unmanned technologies are underdeveloped so far. Therefore, we need better technologies for monitoring and living in such harsh environments. We can do this only step by step. After every step, we need to do verification. So there is a long way to go yet before we start commercial production. We also developed several designs of ship vessels, and you may be able to see the videos later. On this slide, you may appreciate one of the results. We have been doing these experiments for a few years already, processing bulks of statistical data so as to be able to use this data in AI. The back system covers the key positions, and thus it can deliver either monitoring or whatever else. Our designers today are actively working on how to integrate the AI and other technologies. Simulation allows us to develop entry data in order to teach neural networks. We can use the obtained data to have the algorithm, and this allows us to develop agents and to make them cooperate in teams. Thus, we promote teamwork. The results of our activities promote simulation modeling. These results show that these algorithms are viable and quite robust. The students learn how to eliminate limitations, how not to lose information, so on and so forth. Why is that important? It's important because once we start practicing all these technologies in water, and water is an indefinite space, then that's important to have the statistics that we're going to receive Considering that our key area is resolution of practical tasks, we were able to develop a robotic maritime machine. We integrated a few algorithms into this machine, and here you may see the underwater glider. I should also note that the operator control point and onboard control systems are equipped with 100% Russian-made equipment. That's indeed true. And here you can see the experimental design sample. Thus, we were able to publish a set of joint papers and to perform drills jointly with the Emercom of Russia so as to demonstrate how to use gliders to cover 4 large territories. And within this experiment, we had to survey 3 areas, and the task was successfully fulfilled.
Next stage was the experiment as a part of the block of sensors. The parameters that are measured are presented on the slide, like temperature, dissolved oxygen, and so on and so forth. We do direct management and calculations. This sensor was installed at the body of our submersible, and we received necessary results in the bay. And we worked together with Emercom. The conditions were complicated because the area is highly stratified, very different salinity values and strong currents in the region. We tested the overall functioning of our vessel. It completed all necessary missions. We received all necessary profiles with a model of useful load. We measured also the radiation using the special edition. Your time is up. Your time is up, Andrei. And we registered that at the internal data carrier. We verified our comprehensive algorithm at their biological station. We measured profiles using the useful load model, and as a feedback, we showed that our results are comparable with their real measurement results. This is also an example of one of our works to create frontiers of patrolling. Therefore, we implemented a lot of algorithm and functional models that were used at our unmanned vessels and full-size gliders. The software is 100% Russian, by the way, as I said already. Andrei Soykinin, you have the floor. Representing CJSCC project. Please stick to 7 minutes. Colleagues, good afternoon. Yes, my name is Soykin Andrei. I represent C Project company. And I thank you, the organizers, for giving me the opportunity to present our project in the field of unmanned vessels. Let me give you a background information. We felt certain needs of the shipbuilding industry because initially we were developing software. We have another dimension that deals with the development and the construction of heavy-duty machinery for marine purposes, of course. We have a small design bureau, 60 people, and we have several competences within the field of the marine robotics. So joining together 4 dimensions of our corporate activities, we came up to the project of the creation of UMRK Zephyr. Why did we do it? Why did we create it? First, survey and state of evaluation of the underwater pipelines, cables, oil and gas development machines, mapping of the shoreline, control and support of the seabed works, of the dredging works. There are other tasks that were in hand, like gathering of information from different media stations, environmental monitoring, and scientific research. Patrolling of and control of the sea route, retransmission of signals, connectivity, GPS, and for salvage missions, execution of research missions, visual reconnaissance, participation in the liquidation of oil spills. What our cruiser or cutter rather looks like. So we have the cutter itself, the guidance system, additional equipment, and simulation and training complex. It's 5.3 meters long, 1.7 meters large in the largest part, 80 centimeters height. So max speed 35 knots when it carries 200 kilos. Maximum load is 400 kilos, but the speed will be lower. Sea force 3, 100 millimeter displacement. In the basic version, we have 100 liters of 92 petrol. The autonomous range is 400 kilometers, limited by gas reserves. So we have fiberglass body as an engine. We took local engine from Lada. While designing this item, we wanted to make it as Russian as possible. Then should be basic, which means we should be able to add this to that equipment, and it should be cost effective as well. This is necessary in order to expand its utilization. So we have our own water jet engine. The guidance system has been developed by ourselves, quite a large space for additional equipment. Then we have fuel compartment and equipment compartment. The body has 4 compartments. There's a separate access to compartments when two compartments have water. She stays afloat still. The mass center is lower than the water line, closer to the back of the cutter. It's light. We transport it for the tests by a simple remorque. Like you take a couple of guys and you put it afloat on an unequipped shore. From the guidance system, we use AI in order to connect the dots and to execute certain missions. So guidance system, let me talk you through it. The operator operates it, or she can go from one point to another point. Trajectory construction, stable position, return to the base, telemetry data transmission, or accumulation in case of bad connectivity of information, of course. Technical vision, pre-launch checks. What about connectivity? Now on the polygons of the northwestern region and at the far eastern region, we participated in the competition as well. In UH next time, we will use drone in order to extend GSM model is clear. In case of satellite connection, we can do even better. All in all, this concludes my presentation. Thank you for your attention. Thank you, Andrew. Thank you. Ilya Konstanty, Tethys Pro, just a company. Colleagues, good afternoon. Seizing this opportunity, I would like to present my company, what we achieved in the field of the submersibles, and to talk you through our current focuses and development areas. In terms of background information, we started back in 1991 as a vendor. For 20 years, we've been supplying marine robots from foreign companies, Subsea, SMD, which mean leaders of the market. And we accumulated a lot of knowledge, a lot of experience in terms of the market and the robot design. And starting from 2014, we started commercializing our own equipment, Marlin 350, and recently we launched RTPA 100, or rather 1000. Who buy from us? The Ministry of Defense for their fleet. They operate more than 280 units. 100 of them were manufactured by ourselves. The main vector of our development is the following. We maintain our fleet of submersibles because their life cycle ends, they need to be maintained. We are limited in terms of access to foreign spare parts, but since we have the guarantee, we need to guarantee the serviceability of the equipment. We started launching our own solutions and our own products. Our product range will be expanded shortly. We'll produce small products with depth up to 1,000 meters. Same pieces of equipment are in demand by oil and gas companies. It's like the youngsters, if you will, small working class. And we have solutions that we can suggest to the market. Coming back to Marlin 350, this piece was created in 2014 to substitute Falcon. Falcon is the most preponderant piece of equipment at the Russian market. We delivered more than 100 items of this kind. It works at 350 meters. And this is the main piece of equipment for the Russian fleet and for the fleet of our company. We are actively developing accessories. We suggest to install systems of autonomous generation of energy, manipulation complexes with several dimensions of movement and rotation, as well as different hydroacoustic systems. In terms of the development of this item, we have planned the modernization. It will allow us to increase the power of the propulsion unit. It will make this item comply with the oil and gas companies' requirements, like in terms of video quality, in terms of safety and security of the unit, and so on and so forth. Another important endeavor is the modernization of our Panther Plus or TPA 1000. It's a safety equipment, can be transported airborne, and we shipped 8 complexes like this, and most of them have functioned for more than 10 years already. So we modernized it, and we developed 100% made in Russia submersible apparatus. We tested it in the Black Sea with a depth of 1,000 meters, and the tests were 100% successful. We developed Russian propulsion units, manipulation units, video, lighting equipment, as well as guidance, electrical guidance system. This was a big job in order to improve the reliability of the equipment, because now we can isolate defaulted systems. So when the equipment is deep down and one system is off, the overall equipment keeps working. We have our guidance system, as I said, video information treatment systems, and so on and so forth. In terms of future steps, this equipment is not manufactured in big quantities, and we plan to gather feedback from our clients. Like, for instance, recently we received some feedback from oil and gas companies, and we figured out that they need more place on the deck in order to install larger units, and this is what we do in order to give them more space. We modernized this equipment as well in order to make it work deeper. We need to focus our work on improving electric system. Over the horizon of 2026, we see a clear interest and a need to come up with unmanned vessels, but the components of unmanned vessels. The unmanned navigation legislation is developing rapidly, and this time they will need to have submersible robots. This will be our future focus in terms of service, repair of these equipment. Thank you. Thank you very much indeed. Viktor Tarasov from the State Maritime Register. What a subsea apparatus is. Let's talk about law. Yes, the topic of my presentation is the development and improvement of the classification of unmanned underwater apparatus. The development of offshore oil and gas deposits triggered the disruptive growth of submersibles. And the participants, like the developers, the producers, and the operators of unmanned subsea vessels, they asked for the systematization and unification of rules and legislation in order to guarantee the safe utilization of underwater vessels. As for today, the Russian State Maritime Register is a world known entity. Our institution was established back in 1913. We are acknowledged by marine administrations from more than 75 countries. We have a lot of high-skilled experts working in the institution. We have offices within Russia and abroad. Our main goals are the following: improve safety standards, improve safety navigation standards, improvement of safe goods transportation by sea, as well as the development of measures and standards in order to prevent pollution. Take into account all of the above, as well as our experience and the demand from the market participants. We were brave enough to initiate together with Rubin, Malachite, OSK, to develop rules to classify and construct unmanned subsea vessels. Russia started to adapt ghosts with some traits of classification, but these ghosts didn't have any information about technical parameters.
The register and its rules in the classification of unmanned submersible vessels starting from 10 kilos is established to assign specific classification classes to every particular machine. So this register is just the framework for future classification, and it has to be implemented in assigning classes to every submersible vessel. The basic parameter is the hull of the vessel, and here you can see the main classes. According to this register, we have the main class symbol and semiotics, that signs that refer to a particular design. Certification of unmanned submersible vessels is also very clear and is based on design. First, you submit an application with the dossier, all the documents. Then, based on the technical documentation and the positive results of tests, the documents are issued. On top of that, one of the key aspects of the register is research. What we do is coordination of research efforts based on the Research Council. The Research Council is responsible for a variety of areas, such as construction, robotics, including marine robotics, and so on. We anticipate to have the first meeting of this task force in the near future. We also used to participate in different fora, like Army 2023. We also cooperate with other parties and stakeholders, as well as producers of unmanned submersible vessels. One of the key advantages of the register is that this document is enforced and renewed faster than any rules and regulations adopted by the government or any kind of ministry. Considering that this is a very dynamically developing industry, this makes it a keynote advantage. Considering the fast developments, consumers of services sometimes are not aware who is the manufacturer, who is the dealer, and who is the integrator or so-called the moderator of the deal. Therefore, we establish a database of producers that allow us to verify who produced a particular vessel. The service is already available. On top of that, we also have feedback and we develop the rules, and this also facilitates dynamic development. We are ready to dialogue. Everyone is welcome. Thank you, Victor. We would like to invite our colleagues from China. I would like to ask Dima 10 to join us. The shipbuilding university is a good friend of the Harbin shipbuilding university, and we are long-standing partners and friends. Please, Mr. Matan, the floor is yours. Please, let's have our colleagues from China here on the screen together with us.
Hello, can you see my screen? Ni hao. Hello. Am I okay to start? Yes. Yes. Thank you. Hello, everyone. I am Ma Tong from Institute of Shipbuilding and Marine Technique of Harbin Engineering University. It is really my honor to be here to introduce our work of our group in AUV geophysical navigation, especially in the field of terrain-aided navigation. Let's start from the introduction. The objective of achieving prolonged autonomy at sea has been hindered by the errors associated with AUV navigation systems. The resulting navigational error of a dead reckoning navigation system will grow over time, thus rendering them unsuitable for long-endurance navigation missions. Both long baseline and short baseline system can, in principle, provide a bounded navigational error, but the required exchange of acoustic signals between the AUVs and the acoustic arrays will require the AUVs to work in confined areas. As a method which can provide accurate localization results in unknown areas, simultaneous localization and mapping, also known as SLAM, shows its potential for long-term navigational mission. In section 2, I will introduce some detailed works of our group. First, we propose a bathymetric SLAM algorithm using a graph method. In this method, a vehicle will continuously measure the seabed terrain using a multi-beam sonar and estimate its position using a DR system. Loop closures are detected according to the similarity between the current measurement and historical bathymetric data, and then the trajectory of the vehicle, including all historical states of the AUV, will be recalculated according to loop closures. Here we give the framework of the proposed bathymetric SLAM algorithm. First, briefly, this algorithm includes graph construction and graph optimization. In the first one, navigation and bathymetric data are divided into various submaps, and then weak data associations between frames and loop closures between submaps are detected. In the graph optimization, we denote all frames associated with loop closures as keyframes. We optimize position of the vehicle at all keyframes using global trajectory correction. And then we will modify the local trajectory using local trajectory correction. Here are some simulation results. It can be shown that bathymetric SLAM can provide accurate navigational results for the vehicle and build a consistency map. However, this is just a simulation without any invalid loop closures. If we have invalid loop closures in the simulation, the experimental results will be very disappointed, just like the field results in this slide. As the increments of the number of invalid loop closures, the mapping results of the SLAM is becoming more and more disappointed. And due to nearly flat seabed terrain, invalid loop closures are unavoidable in SLAM. So invalid loop closures identification is a very important part to the realization of bathymetric SLAM. To identify invalid loop closures, we proposed the MCM, a robust SLAM algorithm with a greedy method. Here's how the MCM works. If the optimal map consistency exceeds a given value, one of the loop closures will be considered as invalid in current iteration. Validities of all loop closures will be recalculated when a new loop closure is detected, which means that validities of loop closures will change over time. But in the SC experiment, when the fraction of the invalid loop closures increases with the noisy bathymetric measurement, MCM failed and provided inaccurate and unsustainable navigational results. A reason is that a great number of invalid loop closures leads to the misidentification of invalid loop closures, and finally causes large navigational errors. In addition, when an invalid loop closure is considered to be valid, the whole trajectory of the vehicle will be recalculated using the invalid loop closures, and the navigational results might get worse rapidly, making it unstable. So we fuse the MCM results with a priori estimate on the trajectory of the vehicle, propose a robust filter method. Here are the results from an SC experiment. Robust filter, the black line in the figure, has smaller trajectory errors than the MCM. The weakness of the robust filter is the large computational cost. We have to re-identify all loop closures when we have detected one new loop closure. We thought that it would be better if we can keep some of the historical information about the validity of loop closures. Thus, we propose the robust SLAM with PF backend method, which estimates the validity of a loop closure using the particle filter. For one particle, the map consistency is calculated by a global graph optimizer combined with historical trajectory, loop closures, and belief estimations of loop closures stored in this particle. Eventually, the optimized trajectory map is generated using the weighted beliefs of all loop closures. Different from the robust filter, the execution time of the global graph optimization in the PF backend is independent on the number of loop closures and is equal to the number of particles. 3,000 particles in the PF backend can provide more accurate navigational results for the vehicle than the robust filter. Using the field data, we have proved that both the PF backend and the robust filter could provide accurate navigational results for the AUV, but the PF backend is more time-saving. The final section is about our future work. In our opinion, the communication restraint cooperative bathymetric SLAM is quite important, but very difficult. Communicating using the acoustic channel is low bandwidth, high latency, and unreliable, making transmitting a lot of bathymetric data over an acoustic channel very challenging. That's all for today. Thank you all for listening.
Thank you. Well, the School of Maritime Science and Technology is located in Xi'an. Please, let's have our speaker on the screen.
你好，
Can you hear me?
您胜的，您
Okay.
定的。
So I will. Okay. May I start?
OK OK。
Okay. Thank you. Thank you. Hello, everyone. It's very honored to be here to give my talk to you. I'm Jun Wan from Northwestern Polytechnical University, China. Today, my topic is sustaining the drag reduction effect of superhydrophobic surfaces. My talk is divided in 5 parts, so let me start with introduction. Firstly, drag reduction technologies are of great importance for ocean engineering, as it can increase the speed and reduce the energy consumption of underwater vehicles and ships. There's a magic phenomenon in nature for surfaces such as lotus leaf and the leg of water striders. These kind of surfaces are very hard for water to wet them, and we call this phenomenon superhydrophobic. And for a surface to be superhydrophobic, there are 2 criteria. First, no surface free energy, and the second one is micro and nanostructures. Now, in these 2 criteria, researchers have successfully developed many methods to make artificial superhydrophobic surfaces. And technically, superhydrophobic surface is defined as a surface which has a contact angle larger than 150 degrees and a contact angle hysteresis smaller than 10 degrees. And there are 2 wetting states of such surface. The first one is the vernal state. So the water penetrates into the micro and nanostructures, and the solid surface is totally wetted. And the second wetting state is the Casey state. In this state, the water did not totally wet the surface. There are some air pockets or air film between the water and the solid surface. And it is due to this air layer which gives the drag reduction effect of the superhydrophobic surfaces. As you can see in this slide, in the figure on the left, the characters are painted with superhydrophobic coating, and its real color is red. So in air, we can see its real color, it's red, but when we place it underwater, there's an air film on the surface. So you can see it is light reflecting. We cannot see its real color. So in this way, we show you that clearly that there's an air layer on the superhydrophobic surface. And then we tested the drag reduction effect of such surfaces. We found that when the flow speed is small, there's a remarkable drag reduction effect, which can go up to 20%. But as we increase the flow speed, the drag reduction reduces and it can go negative, which means it can increase the drag when the flow speed is very high. And then we also tested it with flat plate. So as you can see in this figure C here, this is a superhydrophobic surface underwater. So the flow speed is small. As you can see, there's an air layer on its surface. It is light reflecting. But when we increase the flow speed, which is the figure on the right, which is figure D, you can see the air film vanishes gradually, and you will see the original color of the superhydrophobic surface. So we know that the main thing to maintain the drag reduction effect is to maintain the air layer of the superhydrophobic surface. What we do is that we develop the 2 methods to maintain the air layer. The first one is an active way. So there's a very unique characteristic of superhydrophobic surface underwater is that it is aerophilic. So which means when an air bubble approaches a superhydrophobic surface underwater, it will stick onto the surface immediately and spread into an air layer. So taking advantage of this, you can see here, there's a small video. We manually injected air onto the underwater superhydrophobic surface. As you can see, the injected air forms an air layer, so it can reduce the drag. While for ordinary hydrophilic plate, it is totally different. When we inject air on hydrophilic plate, it will just flows away due to the buoyancy. So this is the first way. So in this way, we sustain the air layer on the underwater superhydrophobic surface. In this way, It greatly reduces the vertical strength and the shear rate on the surface and shows a strong drag reduction effect. As you can see on the right figure, we maintained the drag reduction rate up to 20% by continuous air injection. And the second way is a passive way of maintaining the air layer. What we do is that we introduce alternate superhydrophobic and hydrophilic patterns on a plate. So between the superhydrophobic and hydrophilic pattern, there is a very big contact angle hysteresis, which means a very large a surface-free energy barrier. And this surface-free energy barrier will strongly confine or pin the three-phase contact line of the air layer there. As you can see in this slide, the water droplets in air and the air bubble underwater, the contact line of the droplets and the air bubble are all constrained by the patterns. So in this way, we introduced this pattern onto a rotor, and we created some annular alternate superhydrophobic and hydrophilic strips on this rotor. And then we manually injected air onto the superhydrophobic strips, so it forms air rings on the rotor. As you can see, it looks like tires, but they are actually air rings. And then we tested the stability of such air rings. So as you can see, the diameter of the radius of the rotor is 25 millimeter, and the rotational speed can go up to 1,500 RPM. So even at such a high rotational speed, the air ring can still sustain. It deforms a bit, but still it can sustain. And then we tested the drag reduction rate of such air rings with a reometer. And the results show that the drag reduction effect can go up to 77%, and the drag reduction increases with the thickness of the air ring. What's more, the air ring not only reduces the frictional drag, it also changes the velocity profile and also the flow structures in the gap flow. And these are all the results we show in my slides, and these are conclusions. I'm not going to read it, but the main work in this talk is that we developed two methods. One is passive, the other one is an active way to maintain the air layer for drag reduction for underwater superhydrophobic surfaces. That's all. Thank you. Thank you very much.
Спасибо.
Thank you very much indeed. I would like to pass the floor to Natalia. She is she represents one of the most practically oriented companies, and she constantly works with different submersible equipment. Firtoen group of companies. Good afternoon, dear participants of the International Strategic Session Marine Robotics. I'm the chief engineer and constructor from the Technical Complex Development Group. My presentation is dedicated to the development and creation of the tele-guided unmanned submersible apparatus. I would like to say a couple of words about our company. Our company is Russkaya Morskaya Komanda, Russian marine team. It's an IT company. We automate processes, create digital twins, and we design and manufacture radio electronic equipment, digital and analog pieces of equipment. In the modern world, the big development is given to the robotics. The products of the marine robotics, like heavy-duty complexes, are used in different spheres. Monitoring of the seabed in order to detect true coordinates of the placement of underwater items that could be potentially dangerous for the navigation. They monitor chemical components in the water. They do necessary surveys in order to better place pipelines, repair works, and as well as liquidation of different consequences of environmental and technogenous catastrophes. Since this topic is gaining its relevance, we decided to create a tele-guided underwater complex. Our engineers did it. First stage was the comparison of existing models of this kind of equipment. The definition of necessary characteristics. We defined the weight, 5 tons, power, 160 horsepower, 3,000 meters depth, 3 knots of speed, and 150 kilos of useful load. At the analytical stage, we defined as well main tactical and technical characteristics. We defined the critical item points and possible procurement opportunities. Okay, unmanned complex developed by us is dedicated to geological surveys, safety works at the depth not exceeding 3,000 meters. It has 3 thrusters of horizontal and vertical movement, 2 manipulators, video cameras, lighting equipment that rotate, and accessories that help to define all nuances of the environment, and the pressure compensation system that protects all internal items from the destruction with strong pressure at big depths. As for today, we designed and we launched 3 main units of this installation. They allow to launch and move our complex, i.e. Pumping unit that has 2 pumps and 1 engine, hydraulic reservoir that compensates for pressure with the preliminary connection with the filter block, and the guidance unit into water protected, or rather water safe body. A special attention was made to the modeling of the guidance system. As for today, we created a mathematical model of the guidance that takes into account all relevant characteristics of the complex, including movement options and the impact of the external environment. The control of the functioning of this complex is performed by the operator from the shore. He or she has the route of the complex on his or her screen. We paid greater attention in order to find the delay of video signal that is being transmitted to the shore. Design works started back in 2022, and we plan to achieve them in fall 2025 with tests, with real tests in the water. This concludes my presentation. Thank you, Natalia. I would like to give the floor to Sergei Popov, representing Peter the Great Polytechnic University's Institute of Computer Science and Technology, with 2 co-authors. Good afternoon, dear colleagues. I would like to present to your attention the visualization of logistic operations in the heterogeneous vessels in case of situational unawareness. This issue of uncertainty is related to the lack of data and information. This issue is linked to different speeds of data obsolescence, time non-synchronizing, not being synchronized. In order to solve this issue, we suggest to come up with an information system based on the virtual or augmented reality that brings together geopositional mapping, meteorological, and radar systems into one essence. To do so, we need to solve three major problems. First, multi-criteria search for navigation of vessels in order to plan operation, the avoidance of collisions in this movement, and 3D visualization based on data. The results should show, or rather construct, the path. Amid a difficult ice condition, we came up with a method. It is based on the integration of several criteria. We bring them together, and on this slide, you can see options of values of strata levels and different trajectories that could be achieved depending on the weight of each method. In order to visualize of the results of the multi-criteria search, we came up with a solution based on a map creation. This map has elements related to absolute uncharted areas, aka no access area for ships, as well as the map based on risks. The red line stands for the route, which is based on the criteria optimization method, based on the ship's displacement, sea depth, and the ice thickness. It takes into account ice class of the ship as well. To avoid collisions, we implement the method of ship divergence based on the navigation rules. An interesting peculiarity of this method is the distribution of opportunities of navigation by decreasing the ship's velocity, but also by changing her trajectory. To have a real imagery, we used initial data as a map under the format of S57, and we took all hydrogeological information from it. We represent the ice situation as well, and the thickness of ice is mentioned as well. We took information about latitudes from open sources, and textures, we took them as well from publicly available sources, which means satellite imagery. To plan the operations, we use different meteorological conditions, day versus night. We factored in rain and snow and mist. We can imitate bad sea based on the 12-point scale. For the visual identification, we built in ship's models. These are high polygonal models. We have an icebreaker, a gas carrier, and we have also Titanic, but it was just a joke. The IT system is a distributed calculation medium. It has a visualization component, a calculation component. It gives a 3D visualization And the system has also a calculation server. Our software is an open code-based software. We use the open software as well. The calculation server works at the heterogeneous cluster of our supercomputer calculation center. To give you an example of the visualization of the milieu, it is capable to create non-collision-free trajectories amid a complicated ice situation. In the future, the system could be used in order to be integrated into on-board IT system. Its main goal will be the systematization and the optimization of the raw data required for the successful visualization. Thank you very much for your attention. Thank you very much indeed. I think I should give the floor to Tansin Ozden from Istanbul Technical University. Can you see me? Yeah, we know him very well. He was in Moscow and he understands Russian very well, correct? And he was at the stage in Moscow. I study Russian, but I'm not ready yet to present in Russia. No, sorry for that. Next time. Next time, correct.
I will talk about two different experimental setups which we developed in Istanbul Technical University. Is this? So our motivation was to develop two different maneuvering setups, and this project was financed by our Presidency of Defense. The first system is a planar motion mechanism, and the second system was a free-running maneuvering system. We developed both systems in our university, and we compare our results with the Simman participants. There were three different planar motion mechanisms in this conference, and one free-running system. Denmark, Italy, and USA was planar motion mechanisms, and Netherlands Marine was the free-running system. So we developed our own system. It is quite modular and has very large amplitudes in comparison to Scotch yoke mechanism, which the other institution has. So here you see a pure yaw experiment in our facility. Here you see some comparison of typical results. We had a very good agreement with our institutions. And although we have a very small scale model, our uncertainty was quite good comparison to United States, maybe. And this system is now actively used in our model basin. Here, in these experiments, we are developing a new method to superpose wave force and moments into maneuvering calculations. And the second part was a free-running maneuvering system. We developed both systems, and we made the benchmark studies on Arleigh class frigate, DTMB 5415, they say. So we made the same experiment on a small model on planar motion mechanism and the same experiment on a free-running system. The free-running system, although you see a remote control here, it is semi-autonomous. So we input the experimental parameters, and the model does the experiment by itself and collect data, which include a mobile unit and a shore station. The model is quite large, 5.7 meters, but the system is very modular inside it. Here you see the control and data acquisition software. One unique thing about this system is it is GPS synchronized. It means we got PPS signals from GPS, and we make it a 10 hertz signal and use it as a hardware interrupt for data collection, which means we have signals for 10 hertz, and we collect all the data from propeller servos, rudder servos, heading, GPS position, etc. And after the experiment finished, we already have the results in our computer. Here you see a turning circle experiment we are conducting on DTMB 5415 model. With the planar motion mechanism, we did experiments for 3 different Froude numbers. One was slow, one a medium speed, and a high speed one. And after doing these free-running experiments, we simulated our results from planar motion and compare it with the free-running mechanisms. And here you see a zigzag test. So the model makes the test by itself. And it is a lake in our university campus. We got very good agreement with Marine. We think actually we did even better than them, because as you can see, with 10 degrees zigzag, there was some problem with their results. And these are interesting figures. As you can see, with the green dashed line, it is the slow speed. It means our results are non-dimensionalized. So the derivatives we got from slow speed is also non-dimensionalized, and it should be independent of speed. But our results show that if we don't do the test with a high speed, then the slow speed derivatives are useless, as you can see in red and green lines. But the orange line is the high speed, and it shows very good agreement with both 18 knots and 30 knot free-running results. We use this experimental free-running setup also on a European Union project called Gators. Our system, free-running system, assembled just in 5 working days on this model, and we made the experiments. Here you see a conventional rudder and a gate rudder. As you can see from the photos, a gate rudder has 2 parts and can turn almost 90 degrees to close the propeller and 15 degrees on the negative side. So we investigated the advantages in terms of maneuvering. This project is big, so they check the acoustic performance, resistance performance, etc. But our focus was on maneuvering performance. So we put our modular free-running system on this model, and we compared the results for both conventional rudder and for gate rudder. We conducted, again, experiments in our lake. We did experiments with both one rudder is moving and the two rudder is moving. And we did the experiments for 35 degrees and more, because a gate rudder can turn much more than a conventional rudder. So we want to compare the results. So as you can see, on the left top, there is the conventional rudder case. On the right top, there is the gate rudder case, but only one rudder is turning. And on the right down image, you see a gate rudder. One of the gate rudders turn minus 15 degrees, and the other turns 35 degrees, which has almost similar results in comparison to the conventional rudder. But as I told, these gate rudders can have much more turning angles than conventional rudder. And as you can see on the down left, gate rudder's performance got better with higher turning angles, rudder angles. And with the zigzag performance, 10-10 zigzag performance, when one rudder is working, the overshoots are smaller, but the period is very large in comparison to conventional rudder. But while two rudders are working simultaneously, then the results is almost similar for 10-10 zigzag performance. But it shows itself better on 20 degrees. So again, the overshoot is quite less than with one rudder moving in comparison to conventional rudder. But the period is also large. But while two rudders are working simultaneously, then the period is good, and the overshoots are even better than the conventional rudder. So here are some conclusions which summarizes our studies. I don't want to go on them. Спасибо большое.
Thank you so much. Thank you. Well, okay. Professor Mohammed Se, Sherry Technical University, he sent his video. So could you please have Professor Se on the screen?
I want to talk about development of the state space model.
Не видно на экране ничего.
Underwater glider in vertical and horizontal planes.
We do not see Professor on the screen. We do not see the video on the screen. We don't see the video on the screen. Please put the video on the screen.
Вот сейчас. Пожалуйста.
Please.
Hello everyone, I'm Ali Hassanman. Today I want to talk about development of the state space model for underwater glider in vertical and horizontal planes. The first section is introduction. So, 71% of Earth's surface is covered by water. Oceans are very important because it includes a source of foods and resources. For these reasons, ocean and seas hold significant importance. Underwater exploration is facilitated by underwater robots, and today they are categorized into various classifications. The application of these robots includes seabed investigation, research, observer, and many other tasks. Under Underwater robots are categorized into two groups from a control perspective. These categories include ROV, AUV, and gliders. Yeah, our underwater gliders are the main categories of underwater robots. So, underwater gliders are very popular for extended endurances caused low energy consumption. And the second section is basic idea. Gliders include two wings for thrust generation, that these are helpful for decreasing of energy consumption. This type of robots don't have any propeller for propulsion and advanced movement by internal actuator. This type of robots have a zigzag-like motion. Buoyancy tank at the near surface start to fulfill and the desired depths start to empty. Then glider began ascent and descent motion. Pitch system adjusting of wing angle of attack for optimization of performance. So, gliders actuator are started when they are near surface or desired depths. Third section is equation of motion. For dynamic of motion, two coordinate systems are defined about ground and center of gravity. For dynamics, rigid body, Coriolis, and damping, restoring terms is considered. Finally, equation of motion are shown in the slide for 6 degree of freedom for underwater glider. Helical maneuver is simulated for sensitivity analysis. Glider was descended with 15 degree of roll and 20 degrees of pitch angle. So the trajectory of vehicle similar to the left plot. Right plot is X-plan perspective. The result of sensitivity analysis are shown in the slide. For example, surge, pitch, and heave motion are illustration in the figure. Indicated that yaw, roll, and sway motion have minimal impacted this motion. Consequently, for an underwater glider could be separated 6 degree of freedom to two model in horizontal and vertical. For vertical model is illustration this slide, and horizontal model illustration that slide. comparison of non-linear model with linear model is presented in the slide that have very match, and we can relate the state space models for controller design, observer design, and other cases. For this section, city glider in Sheriff Pools was tested for validation of the model. This pool has a depth of 3 meters and a length of 50 meters. Left plot compared glider depths between experimental and numerical simulation, and right plot is roll angle, the helical maneuver. That the result had a good match with experimental test. So this study could improve to control design for underwater glider and control of motion. Thanks for your attention.
Спасибо.
Thank you. Professor Saif is the director of the Maritime Technological University of Sheriff in Tehran. So who's the next speaker? Andre, you or someone else? Oh, I'm sorry. Anton Zhilinkov, Dean of the Digital Industrial Technology Faculty, Head of Department, a very prolific author and researcher. I believe that he has got the utmost publications than all of us together, and all of these publications are Q1 and Q2. Oh, you are over-exaggerating. I'm not. I'm just being envious. Okay, thank you so much. Hello, colleagues. I've got just a small-scale presentations to show our results in unmanned submersible vessels used to clean underwater facilities, including underwater structures and vessels. We know very well that vessels and underwater structures are easily exposed to different microorganisms, which increases the fuel consumption and triggers a very negative economic effect. This may also result in demasking factors and may impact the environment as well as the environmental weather transfer, which impedes the environmental situation in the aquifer. We analyzed, and yes, we are very regular participants to such conferences. We have heard many times about the importance of this problem. Currently, the cleaning is done by divers. This job is quite dangerous. So we used several ideas on how could we do that in the future, and we analyzed all the options. Some of our designers participated in these projects, and we analyzed advantages and drawbacks, which I'm going to talk about today. I'll try at least. As a result, if we speak about the cleaning of the vessel hull as opposite to international technologies, our solution allows to clean the hull outside a dry dock, which means during loading and unloading. And on top of that, you can do the cleaning of the vessel while underway without actually coming into the harbor. It is possible to clean the vessel on both sides, and ultimately we've got lots of advantages. This system allowed us to resolve a number of problems. Those were the development of specialized models that allowed us to assess dynamic characteristics, and considering that the drug can operate in both environments, both under surface, and this technology is quite autonomous, and this allowed us to resolve on diagnostics, controlling. Well, actually, we also implemented AI to detect and decipher the state, the condition of the surface to be cleaned. These tasks regarding movement and stay are also resolved. Here we use pneumatic or magnetic system as well as combined systems. Currently, we have implemented the following system. Here you may see the parameters of the technology itself, of the vessel itself. The very project on cleaning the hull was a priority project within the 2030 program of the St. Petersburg Shipbuilding University, jointly with the Mechanics Institute of the Russian Academy of Sciences.
I'll skip this one. This is the example of our test sample. We have our testing wall at Itmer. It moves, it functions. Talking about this solution, and this is a development prototype. We use the water jetting or high-pressure water cleaning, but from the environmental standpoint, it's not the best option. Well, water is the best option, but not sand, because sand jetting can be applied as well. Gazprom Neft ordered this from us, as well as Gazprom Shelf. We developed a item to clean pontoons at the Prirazlomne station. It's a fixed oil development rig. Once again, this item allows, even in case of the cleaning of the hull with the different curvatures that should be avoided by the machine. In case of caissons or caissoons, we need to overcome 90-degree angles. For this, we developed a specific configuration. This is what a technical design of the system looks like. We faced the challenge because the magnet system didn't work, because Prirazlomne is made of a different type of steel. Therefore, we came up the vacuum fixing and movement system, and the robot is flexible in order to overpass and overcome impediments. This concludes my presentation. Thank you for your attention. Thank you very much indeed. And I'll give the floor to Kirill Safronov. Fedorov and Ryzhov are co-authors representing the St. Petersburg State Maritime Technical University. Colleagues, good afternoon. Our presentation is dedicated to the characteristics of sub-border cable-less sensor grids. This is quite a relevant topic because sensor grids start to be used almost everywhere. For instance, to monitor certain environmental values underwater, to follow up commercial ships for other tactical reasons, and for many others. Within our studies and our developments, we had a lot of tasks, like, for instance, to come up with a set of criteria to evaluate the resilience and reliability of the system, and to come up with certain recommendations how to deploy these grids. It's a common knowledge that underwater, normally an acoustic connectivity channel is being used because optical, electromagnetic, and radio types of communication don't penetrate well through water, so they are not adapted to that. Acoustic channels, however, are more reliable. Nevertheless, they have issues that we need to work on, and we integrated and factored these issues in our models. On this slide, you can see a structure of our model and its architecture. We based ourselves on a model with several certain layers. Every layer has its own physical characteristics. The cherry on the pie of the model is that we use as a bus a glider, a wave glider. And for every agent, the mission is to transmit a piece of information to the reference node. This reference node is connected to the glider, which is transferred to the data center. What other characteristics are being taken into account? They are here. The characteristics of emitting and receiving units, routing protocol. We can place sensors differently, and within sensor grids, we can place reference agents arbitrarily. We take into account physical characteristics of the environment that impacts the signal transmission. First of all, the muddiness of water that gradually kills the signal. Based on the above-mentioned characteristics, we developed a comprehensive metric of connectivity. It's a value that includes all parameters available, and based on this figure, we can calculate the probability of the successful transmission of information between two adjacent sensors. Optimization criteria that we picked. The first one is the reliability, an overall percentage of lost messages, so-called PLR, and the energy efficiency criteria. Here you can see several examples of the reference sensors positioning. We had 4 cases. Every case has been evaluated and conclusions have been formulated. It's not C, but wave glider, it means that glider passes over sensors, which means its trajectory either coincides if it's a perimeter positioning or line positioning, or the sensor, the glider rather, will have this serpent movement between different dots. We came up with analytical results of the grid. Moreover, we, on top of that, added a simulation, which means computer modeling. Some examples of analytical results are presented here. We analyzed the larger and smaller grids in terms of number of sensors, and we found an optimum position of reference sensors. And we saw that for little grids, the best positioning is on one side, along one side. Actually, for the big one, it's the same. Simulation modeling has been performed as well. We invited our students to participate. It's an option for them to participate in a project and to use this information to write their bachelor's thesis. So we compared the real-life data and the analytical data, and they were completely the same. We searched for an alternative positioning of sensors and an alternative movement trajectory of the glider. For instance, we set up that the glider should be following a route with a certain length, but this route should be looped. And thanks to several parameters, we came up with an optimal trajectory. The follow-up task was to assess the impact of technical and topological characteristics, which means the working environment and the distance between sensors. These are quite interesting results, and they are easy to explain. But this is a work in progress. Another task was set. We need to figure out the optimum number of sensors for a specific aquatic area. And here we can see the energy consumption in relation to the predefined number of sensors. So if it's the big distance, we have a low probability of message transfer, and therefore there will be a lot of expenses in terms of resending of the messages. So the optimum version is somewhere in the middle. Our actual works include the following. Keep learning the interference of technical parameters on the grid's functioning. We want to evaluate energy consumption with a predefined lost messages, which means coincide two criteria, and to show their interdependence and interconnectivity. We want to keep working with the simulation models with the use of genetic algorithm. We need to take into account the collisions while transferring packages. We need to take a look at the uneven probability jump and the irregular positioning of sensors. Thank you for your attention. This concludes my presentation. Thank you, Kirill, for your presentation. I give the floor to Konstantin Senchik, first-degree captain, professor, head of marine medical robotics, and he still operates as a surgeon, by the way. Dear colleagues, thank you for this invitation. The story of medical robotics started at the moment of the creation of a first robot. The word robot came from a paper of Karl Čapek. Robot in Czech means a body, so it's like a machine uprising. What's the difference between a robot and a simple machine? Our standpoint is the following. Subjectivity is the answer. We know that there's an object, there's a subject. if a subject acts, an object doesn't act, doesn't perform an action. This brings us to the idea that a robot, since it has its subjectivity, it has to have an intellect, or rather intelligence. It has to have an intelligence. Artificial intelligence became a household name. And an official definition of an AI is presented on the screen. It's way too long and messy. We think that artificial intelligence is a subjectivity implemented within a machine. There are execution mechanisms, which means tools. What's the difference between the culture and the nature? The culture uses tools, which means things created by a human being. These are Roman tools that were extracted recently from the Tiber River seabed. It's not very much different from the tools that we use and the modern medical robots use. If we classify existing robots based on their level of subjectivity, we separate them into three categories: Pro Robota, Robota Vera, and Robota Magna. Robota Magna needs to have 100% subjectivity, which means needs to have an artificial intelligence. But we don't have them yet. Why medical marine robotics? Heraclitus used to say that war is the father of all things. For us, the sea is the father of all things. Marine robotics was the third to emerge. This is a so-called Da Vinci 5.0 robot. What was the purpose of the first robots, Da Vinci-like? The Navy, the U.S. Navy, 40 years ago, had the first startup when they tried to do surgeon interventions aboard the submarine. So in order to keep the submarine concealed underwater and not to transport the injured person, they tried to do it on board. So a startup tried to guarantee manipulations remotely. It was not possible. It was a fail because they had no possibility to transmit information. Everyone uses robot as a term. It's not a robot. It's a copying manipulator. It has technical vision, the only feature that brings it closer to a robot, but its subjectivity or subjectiveness is close or equal to 0. Then, not only ultrasound equipment is the most efficient and guidable tool. The best one is light. Light almost has no weight. It's manageable, and photon medicine is a dimension that develops very actively. It can be applied in the Navy, and it is being applied at the Navy because we have this huge challenge. Yes, seamen have very good health, but should they go over the board, specifically in the cold water, they suffer from hypothermia. 5 minutes in the cold water could kill. The level of hypothermia received kills him or her, even if he or she is being placed back on board in a living state. We cannot, we warm a person from outside, but we don't warm something that should be warmed from the inside, like heart, so light can heart. We have pumps that transfer blood. They are almost robotized. Well, they are reaching this level to the second class, Robot Vera. The connection with the marine robotics. Why? Because inside we have blood, and blood is almost identical to the sea water. There are robots that perform in case of cardiac arrest. It's massage. Even physically strong man can massage only during 6 to 7 minutes because it gets tired. But this person can be substituted by quite an uncomplicated piece of machinery, and it's being done as we speak. And this piece can be used at the Navy and in commercial fleets in order to provide assistance to victims.
The equipment is there. We have already tested it. This is the automatic Magna robot, an integrated diagnostics and ablation robot, including sonography, Doppler, sonographic ablator, the manipulator, and the respective software. It's kind of curative, therapy, diagnostics. And by bringing those two together, we call such devices as theranostics, meaning that there is a treatment and there is diagnostics together. Marine bioexperiments have a very long history. This is one of the most exciting cases. This is an attempt to connect a dog to an underwater robot. Well, I believe that it was amid the Cold War. It was a sort of a fake project, and those who participated in that were not committed to getting any results, as a matter of fact. And practical issues. There is specific technology to evacuate and resuscitate the casualties at sea or those who are lost at sea. And this can be done by autonomous, remotely controlled systems. Thank you very much for attention. Our next speaker is Kirill Rojdestrinsky. Well, I would like to extend my gratitude to Konstantin for making our topic so much humane, because Oleg used to talk about non-humane machines. And that's important, indeed. And now I would like to provide some entertainment to you. And I'm sorry that my presentation is in English. I meant just to have this presentation for our international colleagues. I'm going to talk about the concept of a marine robot based on the principle of pumped hydrofoil. This is the principles that Armen Belkanyan and myself would like to elaborate today. What you see here is very well familiar to us all. This is water sport, a very popular one. And look what it is like. It's a surfer board at a specific shaft, and it is joined to the tandem device. So a person jumps on the board and starts pumping it. Well, you need some skill to be able to do that, but if you master this technique, you can just float above water without going down. So we decided to make a robot based on this system. This is kind of a system that should establish some kind of a force. And this force originates from the tandem technology. And on the other hand, there is a dynamic weight support. This is what we had to consider when developing this model. So here you may see what this technology looks like. This rider makes two types of movements. There's the vertical tilting and the angle of attack. So you can see that there is a combination of oscillations. There is only one mode, and there is the cruising mode, which corresponds to equality of thrust and drag. And you can see that the wings are spread in order to create the dragging force. The Frodo number is large. This is the relative velocity divided by square root GL. At such Frodo numbers, you may somehow disregard the angles. And you see that the cruiser mode corresponds to resistance and the drag. When we do the pumping, there is damping and there is inertia. And these two parameters depend on our motion. And the second is the pumping itself, the tilting of the board. Those are very important parameters. Quite often you do not consider the dynamic sustaining of the weight. And all of a sudden you have the non-dimensional equation system. You can see the forced heaving oscillation of the pumped foil. You can see the dynamic support of the weight and the lift force expended for kinematic parameters. Well, here we may have the geometric parameters. And look what we have. Normally, we have just a regular mechanic system. This is just the forced oscillation of mass on a string. And you can see that there is the damping. And the 2 beta demonstrates the final forced heaving oscillation equation. This coefficient, the square coefficient, is very important. Here you may see that there is a specific force that works like a spring. And right away, this allows you to do various kinds of conclusions. And ultimately, here you can see the delta. Here you may have just an analytical solution. And you can see the overall effect. If it moves from beneath to the surface, there is a self-stabilization effect, and it was very smartly used by Mr. Alexeyev. And here we can see this effect playing the key role. It plays the key role of a spring. And if everything is done correctly by the rider would not suck into the water. Well, we looked at practical parameters, specific equations, and all those are available in the market. How do we calculate the relative frequencies? Well, we can calculate those if the resistance is equal to the drag. Then we can find the frequencies. To the right, you can see how the spring-like movements start and then oscillation starts. The oscillation amplitudes are exaggerated here. And I've got just some numbers here for different rider weights. So this equation allows you to use the Sukhali numbers and identify the velocity that is required to sustain movement, meaning that it's quite from 5 to 7 meters per second, but the frequencies are quite high as well, 2.7 hertz. That's quite a lot. So it's like the previous speaker said, it's very difficult to pump the heart, to launch the heart. And the record was 30 minutes. That was the record number. So if we look at that, then we can also use a robot instead of a rider. And we would be able to use that to create the force of the drag and use different cinematic equations to ensure that. Well, this is the overall idea. There are more exciting ideas, of course, and the more detailed ideas. Thank you very much for attention.
Нет, еще погоди. Мы хотим сначала.
Well, just wait. We want to wrap up this first. We are going to have yet another presentation by Alexander Sokolov. He's a little bit beyond the framework of our topic. I would like to give the floor to Vladimir Nikitin, who was able to come to us. He's a very well-known personality in shipbuilding. He's one of the Doctor of Sciences in the North. He was the director of the Star manufacturing facility. And on top of that, he's also an advisor to VSK. He's also president of the Research Society of Shipbuilders, named after Krylov. Thank you. I represent the International Society of Krylov, and today we are very much into the issues of marine robotics. 2 years ago, we used to have a similar conference, and since then, we have hosted lots of conferences in St. Petersburg, Marine Technical University, and many other venues. Today we are having Mr. Vlasov, Mr. Semyonov, who are the lead designers. And I'm so happy to be amid the research and academic society of St. Petersburg and Moscow and other cities of all Russia. And today, such design organizations as Rubin and Malachite are being joined by other enterprises. For example, the Enterprise for Shipbuilding. And they just jumped into the work that used to be done by Aurora and many other enterprises. Therefore, it is important to actively participate in what is going on. Therefore, we believe that these issues allow us to consider certification, rules and regulations, registrations, so on and so forth, and also unification and integration. if we have some specific technical requirements, this would allow us to more successfully resolve issues related to modular construction and design. I'm so much grateful to the registers and to you that you, as a head of this task force, were able to do all their job. The Center by Krylov has got all the required capacities and propulsive equipment. Everything that we have developed by now should embrace new materials, including the Arctic, and new technologies. Our 2 days meeting brings together different kinds of dimensions, and it allows us to implement all our ideas. Thank you very much. Once again, thank you for the invitation here, and we are so much grateful to Rubin and St. Petersburg Marian University.
Alexander.
Before giving the floor to Alexander Sokolov, who is with us, he has been sent a foresight of technological roadmap. I would like just to say 2 words to wrap up our subject. I would like to thank our speakers, our experts. I would like to thank all people present here in the room, and I would like to specifically thank the program director, Anastasia and Anna, because they guaranteed this event, and we thank Niva, who will keep being a fantastical platform to discuss. Well, a round of applause to the ladies. And I would like to give now the floor to Alexander Sokolov. Will you be okay with 7-10 minutes? And this is the last presentation for today, by the way. Could you please put on my presentation on the screen? Dmitry Kulakov, where are you? I represent the High School of Economics, and maybe I will try to bring another dimension. Dmitry Kulakov, by the way, technical secretary of our section. Please check the slides. I'll start from a different. You mentioned uncertainty or turbulence. Amid those conditions, it becomes more and more difficult to forecast, specifically to come up with a take on strategic development, take into account input substitution and other modern events. I would like to talk to you about 2 tools that help to build up these strategies for technical development. First is called foresight, the second is called roadmap. Foresight is something that is well known. We've been doing that for more than 20 years. There are a lot of different definitions, but in a nutshell, you bring stakeholders and experts in a field. You bring decision makers, and in the future, probably decisions will be numerous. They pick one consensus option, and they try to come up with a set of steps in order to achieve the result. The logic is a market pull. You analyze existing global challenges, that define the ways how the society and economy will develop. Based on that, you evaluate emerging markets and the development of existing markets. On the next step, you pinpoint technologies that will make those markets successful, and based on that, you pick strategic development priorities. Foresight is a science per se. There are hundreds of papers published every day with monographies and articles every single year. It is indeed a well-developed knowledge area. But we start with the so-called STEEPV analysis. We analyze global trends, social, environmental, financial trends, trends related to a person's value system and hierarchy. I will give several examples. 6 years ago, together with the Krylov Scientific Center, we forecasted the situation in the shipbuilding industry, so I'll make reference to it, but these data date 6 years from now. So we analyze it based on the big data. I'll say a couple of words later if I have time. And it helps us to define not only major technologies, but it allows us to take a look at trends like grow leaders, or emerging trends, bottom right corner, trends where we don't feel a lot of value, but this value grows exponentially. Those global trends, they can be broken down till quite narrow subjects. I'll not elaborate on that because I don't have much time left. Each trend is detailed into smaller trends, and their impact on technologies, on the market development, is being analyzed separately. These are pictures from our forecast together with Krylov Institute, and we were wondering what new types of ships and new technical solutions could potentially emerge in future. Next step is the market evaluation. We evaluate the global shipbuilding market. These markets are detailed, and for instance, for several types of vessels, we evaluate separate markets, and till 2016 we evaluated existed markets, and then we had several bifurcations. This is another example from the aerial industry. We can also take a look at emerging trends based on the startups analysis. Our system allows us to do so. We pinpoint startups that could potentially have interesting solutions, and this could allow to determine trends. Another example, well, once markets are evaluated, next step is to evaluate the technology. And here we take a look at existing technologies. That's the core circle, the middle circle. These are technologies that are now actively used. Next circle are the technologies of tomorrow, and the outer circle stands for technologies that will be available in 10 years from now. Another result is the line of future events. This is an example from the fuller robotics, not the up-to-date one, but those are events that happened or that will happen. And this picture, well, it's an A3 format. You can see an overall trend of an industry development. It is yet again a visual output that helps make decisions. Let me talk you through strategic roadmaps. A foresight study help you to understand the overall image of the future. The technological roadmap gives you a tool for you to understand the trajectory, how to achieve this future. It could be a company, an economy sector, a group of companies. So it accomplishes several functions like forecasting of the market niches, of the market image, the future deviations. You can take strategic investment decisions based on that, and you can ensure project management as well. Technological roadmaps could be completely different for R&D or comprehensive ones that bring together different ideas. Managerial is possible as well. Main stages, as in foresight, we start with trend setting, with trend definition rather. Then we analyze the markets, we analyze the alternative sources of consumer characteristics. When you see the market and the products separately, you understand that the same tasks can be solved using different products. And based on this fact, you can evaluate whether your industry is in danger or not, because your competitors do something new and you don't. And your competitors think is more interesting for the consumer. And the analysis of existing products. It's a visual representation. We have done more than 100 different roadmaps for many different industries. The map should be read from left to the right, should be created from left to right and read from right to left to define the markets and the products that could be successful. An important task is the market substitution. Technological roadmaps can be used in order to evaluate import substitution probabilities and possibilities, to see what we are lacking of and what tools should be used in terms of management and cooperation with vendors. It's easy to use, it's flexible, it has qualitative and quantitative analytics, and in 15 minutes you can convince anyone or explain the future steps. Let me talk about our I4A system. We've been developing it for more than 10 years ago. It's a very important system. It has more than 800 million documents with all patents, scientific papers, academic analysis in order to evaluate skills and competences. In order to evaluate which skills and competences should be given to employees to be competitive at a labor market. We use it actively. Towards we implemented more than 100 foresight projects in terms of AI or artificial meat, Gazprom's projects, oil and gas development, shipbuilding, ship construction. This concludes my presentation. If you want to have more details in an informal setting, I'm ready to do so. Thank you. Thank you, Alexander. Now we know that we have the future. We have the chair of the future. Dear colleagues, thank you very much once again. Thanks, Niva, and see you next time. Bye.